Hello, and welcome to Rational Functions. Rational Functions, Intermediate Algebra View. So we're going to take a look at just one small item in this lecture, and we're going to look at the domain of a rational function. So first of all, what is a rational function? Let's start with the basics here. A rational expression is an expression of the form p of x over q of x, where both p of x and q of x are polynomials, but q of x is not the zero polynomial. It can't be the zero polynomial. The domain of a rational function consists of those values of x such that the denominator polynomial is not zero. Okay, let's rewrite that. Let's take that as a fact right here. The domain of a rational function consists of all real numbers except those that make the denominator zero. So all we have to focus on for rational functions is this denominator for the domain. And the steps to finding the domain of a rational function, we'll focus only on the denominator. We'll factor it completely, and then set the factors not equal to zero and solve. Let me show you what I mean in our first example. All right, so find the domain. Focus only on the denominator, x. Factor that completely. That's factored. It cannot be zero. That's my domain. In fancy ways, this is the set of all x such that x is not equal to zero. This is actually called set notation, not fancy notation. I call it fancy notation because it has squiggly brackets, but set notation. But interval notation, right? The domain is everything except zero. So how do we say that? Think about a number line. All right, here's a number line. Here's 0. Here's 1. Here's -1. And all we want to do is just take out 0. I can't use 0. So in interval notation, we would say it goes from -infinity to 0, but then we want to pluck that one out. Just that one value. In the entire number line, we pluck out 0. So in interval notation, x not equal to 0 is written like this: -infinity to 0, comma, or a union, 0 to infinity. The comma is better because it's not actually... There's reasons above, really, what I want to talk about in this video, why you really shouldn't use the union symbol. You should use a comma. Okay, so there's the fancy set notation, and there's the interval notation, and most frequently the interval notation is the one that you should look for. Okay, so focus only on the denominator, x plus 7 already factored. This cannot be 0. Solving a not equal to equation has the same rules. Let's subtract 7 from both sides. I'm going to take my answer up here. X can't be -7. So now we think of that number line again, and it goes from -infinity all the way to -7. We're going to pluck that one out, but we can use all the rest of these values. We can use anything we want except -7. All right, so probably, since you're probably pretty smart. I mean, you're watching videos, right, to learn, so that's awesome. X plus 9 can't be 0, which means x can't be -9. Fantastic. So we take this number line from -infinity to +infinity, and we pluck out -9. Make sure you have your commas in all the right places. Interval from -infinity to -9, but we can't use it. Right? Parentheses, we can't use it. But we could start again right after -9. So we could use -9.000000001, and we could use -8.9999999999999, but we can't use -9 itself. All right, that's enough of the annoying nines and zeros. My dog groaning in the background agrees, so let's move on. We'll focus only on the denominator. The denominator is already factored, and it can't be 0. Remember that 0 factor property we had? Not equal to 0. It is factored, so now we use the property. And the property is the same whether it equals 0 or it doesn't equal 0. If two things are multiplied and they don't come out to be 0, then neither one of them is 0 to start with. Same as if I would have had equals 0. We subtract 1. And divide by 2. Over here, we will subtract, let's add 4 to both sides. I'm going to write it down so I don't make that mistake. And if we're telling what x can't be, right, and that's assumed x is everything except those two values. But now think about our number line here. On our number line, we have -1/2 and we have 4, and we want to pluck those two values out. We can't use those. And if we can't use those, that means our answer will be from -infinity to a -1/2, and then from a -1/2 to 4, and then the other side of 4, so 4 to infinity. So if it helps, put it on this number line and see what it looks like to pluck it out, and then you know you have 1, 2, 3 regions that you need to talk about in your answer. All right, let's keep going. Let's do some more. Looks like I could use a little more room here, so let's make that room happen. All right. Let's use blue on this one. Focus only on the denominator. Oh, look at that. They're the same. It's so tempting to cancel those. Don't do it. Don't do it. Don't cancel those, because we need to know the denominator itself before we do anything to the function. We look at the denominator not equal to 0. In later videos, we're going to talk about what we do in this situation and what it means for the graph. Might be a college algebra topic, but I'll get to it eventually. All right, but for now, we ignore the numerator completely. We don't care. We start with the original function and we look only at the denominator. If two things cannot multiply and cannot be 0, then individually neither one of them can be 0. The first one is the easiest. We'll add 3. In the second one, let's subtract 11 and then divide by 5. And I'm thinking on my number line here. All right, write it down every time if you need to. All right, some of us are visual. Some you just need to kind of do steps in order to see what's going on. Some of us just find a method. Find something that works for you every time. We know we cannot use those values. So what are those intervals looking like? -infinity to a -11/5. We use the curly brackets, I call them round brackets, the parentheses, to indicate we can't actually use that value. And then start there and go to our next value. I almost said our another value. That's weird. And finish it out to infinity. You can do this. You can absolutely do this. I'm a big fan on paper. I'm a big fan of this answer. But if you're using online homework service system, as I do for my students, then you'll want to know the interval notation. They prefer that answer. All right. Now, we've done all the steps leading up to this. Let's pick a new color here. I'm getting bored. Let's go orange. What do? We don't care about the numerator. We focus only on the denominator. Denominator cannot be 0. So we factor, take an x out. Why did I take an x out? Only 2 terms, so I know it's going to be a special factoring idea. And if there's an x in both terms, that's the easiest thing to do. Take it out first, see what remains. I always look for the greatest common factor. Well, then x can't be 0. And x plus 2 can't be 0. When I subtract 2 from both sides, x can't be -2. So in interval notation, let me see, -2 comes first and then 0 on my number line. So I'm going to have -infinity to -2. Order matters. -2 to 0, 0 to infinity. Keep in mind, every interval I've written here, the smaller value is always on the left. So from -infinity to -2, and then -2 to 0. I would never write this interval as 0 to -2. That's not an interval, that's a point. All right, so make sure your intervals are always from left to right, always writing in that direction. All right, looks like I put example 7 on the next page, and this one is a doozy. Okay, it needs its own page. This one looks like it's going to be royalty, so let's put it in purple. All right, 6x squared minus 7x minus 20 cannot be 0. And I know what you're thinking. We have to factor that? Or, oh, we get to factor that. That's it. That's the only two options. Yes, rational functions will require a great deal of factoring. So if you need to go back and watch some of those factoring videos, you should do so. All right, how am I going to factor this? I'm going to multiply 6 times a negative 20 to get a negative 120. I need to multiply to be a negative 120 and add to be a negative 7. So I'm just going to write down things that multiply to be 120 for now. I'm not going to think it too hard. I'm just going to go 1, 2, 3. Does 3 go into there? Yeah. 4, 5. 5 goes into 12 twice. Bring down to 2, 20, 25. I knew that. That's not right. 5 quarters? I don't think so. Oh my goodness. Why am I just not getting this right? And if you're having a mental, a day where things aren't working out for you as well as you would like them to, I swear I know this answer. 24. Duh. 4 goes into 20. Okay. 6 goes in 20 times, and I can keep going. I have to keep going. All right, and I'm looking, if I multiply and I get a negative, and I want to add to get a negative, that bigger one's going to be a negative. But here I'm still 14 away, so it's got to be closer. So 7 doesn't, 8. Does 8 go into 120? Yep, 15 times. Hey, look at that. What do you notice about the 8 and the 15? They give us a difference of 7. So we had to work for it, right? That took some effort. But we could power our way through it always. If it adds to be a negative, let me back up. If it multiplies to be a negative, they're going to have opposite signs. If they add to be a negative, the bigger one is a negative. If they add to be a positive, the smaller one is negative. All right, so these two numbers that we had to work so hard to find, we use those to rewrite the 7. So we'll say plus 8x minus 15x minus 20 cannot be 0. And then we factor by grouping these first two, a 6x and a 6x squared and an 8x. Looks like they have 2x in common. I'm left with 3x plus 4. I'll use this negative sign in the middle. 15x and 20 have a 5 in common. But remember, I'm dividing by negative 5 here. So negative 15x divided by a negative 5 is 3x. Negative 20 divided by a negative 5 is plus 4. And these are not equal to 0. And what do we have? Look at that. The 3x plus 4s. That's what we wanted. Those things in parentheses. That's our new common factor. And we're left with 2x minus 5. Seriously, rational functions, it's really all about factoring. We'll use so much factoring in this section. It is absolutely worth going back and reviewing if you need to. If two things multiply and do not give me 0, because let's focus, we're still on the domain here. 3, then each one individually cannot be 0. Let's subtract 4. Let's divide by 3. So we'll get x equals negative 4/3. On the second one, we'll add 5 to both sides. Oh, look what I did here. I forgot my not equal to. That's the danger sometimes. All right, and then we'll divide by 2. Now I know my negative comes first on my number line, right? Negatives, it's always smaller to larger. So I'm going to put them here in general reference. So I know my interval will be from negative infinity to negative 4/3, from negative 4/3 to 5/2, and then again from 5/2 to infinity. That is our domain. Remember, that's all we're looking at in this particular section, the domain of rational functions. All right, you got this. All right, just brings back factoring, a little bit of shell shock. You get over it, because I know for a fact that my students did really well at factoring. So if you're one of my students right now, you got this. You totally got this. If you're not one of my students right now, go back and listen to the factoring videos, and then you've got this. You could do this. Factoring, straightforward. It's just a procedure. All right, it's not a guess and check. It's a procedure. All right, that's it. Thanks for listening.